Well, hi, hello, namaskaram. Myself Mahesh Prasad from Department of Physics. As you know, well, dear students, we are in a chapter. That is a new chapter which we are going to deal. That is nothing but kinetic theory of gases. Well, the behavior of the gas molecules we have described so far in terms of macroscopic molecules or macroscopic in the sense what the kind of large scale we have discussed, like we have seen by using different parameters like pressure, volume, temperature. By using these kind of variables we have discussed many concepts under the concept of different gas molecules in thermodynamics chapter as well, and thermal properties of matter. So far we have discussed in terms of macroscopic scale. Now it is a topic where we supposed to discuss in terms of microscopic scale. In the sense what we supposed to deal all the gas molecules in terms of its speed, velocity, what could be the speed of the gas molecule, what could be the velocity, what could be the momentum, and what is the kinetic energy. All those things we'll discuss in the particular chapter. Okay. And when you see the word kinetic, what comes to your mind? Obviously, kinetic energy, kind of concept that you know, that is a kind like kinetic energy, potential energy. What do you mean by kinetic energy, by the way? It's the energy possessed due to the motion of the particle. Similarly, if we speak about a solid particle or a solid, don't you think a solid is which consists of n number of molecules over there? Yes. But think about how it's constructed, how it is bound each other. It is tightly bound each and every molecule in the particular solid, which is nothing but bounded very tightly. Are you getting? Well, and do you think whenever I give a heat, for example, if I take this as a solid over here, when I start heating, what happens? Don't you think? Do you think its molecule is going to move from one point to another point? No. The thing is, whenever a heat is applied to the particular solid, it is going to vibrate about its mean position. Are you getting? It is just the vibration will take place, and the molecules is not going to move from one point to another point. This we can expect in terms of solid particle, right? Well, and this is a solid we can expect. Well, and similarly, if you speak about liquid, what comes to your mind? Do you think liquid? Obviously, you can think that liquid is kind of the free in the sense we can expect the bond between the two molecules comparatively lesser than how it was in a solid. Yes or no? Similarly, whenever you give a heat to any particular liquid, don't you think its molecule can move? No. The thing is, molecule is slightly can move, but it's not as much as your solid over there. Are you getting? So this is what exactly you can expect in terms of liquid, but we are mainly interested in the gas molecules, the gas particle. What do you mean by molecules, by the way? It is a kind of number of atoms which is constructed over there. Are you getting? Well, so if we speak about the molecular arrangement of your gas molecules, do you think what would be the interatomic force we can expect? They are widely separated. Well, so if you speak about the gas molecules, obviously the interatomic force, if I speak, it is very less compared to liquid as well as solid. In solid we can expect interatomic distance as well as interatomic distance is very much closer, so that it can experience a great interatomic force. And think about a liquid over here, liquid can experience less interatomic force than your solid over here. And similarly, we can expect the gas molecules over here. Gas molecules can experience very less interatomic distance or interatomic force as well as compared to solid as well as liquid. Well, okay. And this is what exactly we can expect under solid, liquid as well as gases. Now we will have some idea on the law which we have seen so far. That is nothing but The first law we can expect, that is, let us start with here, that is Boyle's law. That is the Boyle's law. What do you mean by Boyle's law, by the way? The Boyle's law, which indicates what? It's a law in which we can expect at constant temperature. At constant temperature, what we can expect? At constant temperature. At constant temperature in a particular gas, we can expect and this Boyle, which is observed was that when he kept a chamber or a cylinder at the constant temperature, we can expect your pressure is inversely proportional to volume. Are you getting? So this is what exactly he observed over there. And one more thing we can expect, or we can write PV, which is equal to constant. Are you getting? So this is what exactly it is observed by your Boyle over here. And what he says? At constant temperature, your pressure is inversely proportional to volume in the particular cylinder. So which is equal to, so if I bring V to the other side, what happens? PV is equal to constant. So this is what exactly we can expect under Boyle's law. Well, okay. Similarly, we can take the one more law, that is nothing but Charles' law. That is Charles' law we can expect. What do you mean by Charles' law? Charles' law, what he said was at constant pressure, at constant pressure, what we can expect? At constant pressure, what we observed was that the volume is directly proportional to temperature. At constant pressure, volume is directly proportional to temperature, or we can write this is nothing but V by T, which is equal to constant. Are you getting? Are you getting? So this is what exactly we can expect under the concept of your Charles law over here. Now, and this is also can be taken as, we can take it as that is V1 by T1, which is equal to V2. No, this can be taken as, for time being, we can take it as a V by T as a constant, and that we'll discuss later in terms of whenever we are studying in terms of ideal gas equation. Okay. Well, so the next law we can expect, that is nothing but we can expect the Gay-Lussac law, because each law is important, so that's why we are recollecting the concept to understand more about kinetic theory. Well, according to Gay-Lussac law, what we said? We said at constant volume, we can expect, at constant volume what we can expect? Pressure is directly proportional to temperature. Pressure is directly proportional to temperature. So if it is so, what we can write? That is nothing but P by T is equal to the constant I can write. Well, so this is a basic concept which is explained by three different scientists like Boyle, Charles, and your Gay-Lussac law. And if your gas obeys Boyle's law, Charles law, and Gay-Lussac law, then we can call it as that particular gas which belongs to ideal gas. What do you mean by ideal gas? If the gas obeys the three different laws like Boyle's law, Charles law, and Gay-Lussac law, then we can call it as that particular gas molecules, we can call it as ideal gas. So keep remember this. Now we will study about ideal gas equation. Well, we'll see how to get the ideal gas equation. Okay? Well, that is ideal gas equation. And also we'll see what would be the ideal gas relation with respect to the Boltzmann constant, Avogadro number, as well as universal gas constant. Well, so ideal gas equation, if you want to get, we need to have eye on the topic like Boyle's law as well as Charles law. So by using the Boyle's law, can I write this equation as P1 V1 which is equal to P2 V2 at constant temperature. Similarly, at constant pressure, I can write it as V1 T1 is equal to V2 by T2. So this is the basic equation I can explain. Similarly, I take to get ideal gas equation, if I take at constant temperature, if I take for time being P1, V1, T1 is the initial pressure, volume and temperature. Now if I make at constant temperature, what happens? Obviously pressure will vary from P1 to P2 and your volume can also vary from V1 to V1 dash. I can take. For time being, it is a P1, V1, T1 is the initial pressure, volume and temperature. Now if I speak about a constant temperature, at constant temperature T1, V1 is going to vary to P2 and V1 is vary to V1 dash. So if it is so, since I have taken a constant temperature, which law I supposed to consider? Obviously you can expect the Boyle's law over here, yes or no? Yes. So now I take a Boyle's law, that is nothing but P1 V1 which is equal to P2 V1 dash. I take it as the equation 1 over here. Okay. So now what I do here is that the next step I will keep pressure as a constant by keeping the pressure constant. What I can take? I will take this equation, that is nothing but that is V1 dash divided by T1 which is equal to pressure can be, volume can be V2 and temperature is varied from T1 to T2. So this is what exactly I can expect. Now with respect to V1 dash, what I can write over here, with respect to V1 dash, I can take V1 dash is equal to, that is T1 V2 divided by T2. Let us say it is equation 2. Substitute equation 2 in equation 1, what we can expect? So I can write like P1 V1 which is equal to P2 of V1 dash can be replaced by what over here? That is very simple. That is T1 V2 divided by T2. Now I will bring this T1 to the other side. What happens? So it looks like P1 V1 divided by T1 which is equal to P2 V2 divided by T2. It looks like a scenario like what we had. V1 by T1 is equal to V2 by T2 and this can be taken as V1 by V by T as a constant. Similarly, I can take PV by T which is equal to constant. Well, and this constant we can call it as universal gas constant, or else we can write that is nothing but PV which is equal to R into T, where R we can call it as universal gas constant. Universal gas, you substitute the value, that is the pressure as a standard value, you can take volume also, you can take standard value, and the T value also you can take a standard value like 273, and here pressure 1.03 into the power minus 5 Pascal, and volume at 1 STP. So now if you substitute all the values, I can get the value of R can be, that is R which is equal to, that is 8.31. What would be the SI? PV is a joule, that is joule per Kelvin, joule per mole per Kelvin. So this is what exactly we can expect about the mole in the sense. For time being, if I have, for time being, I consider this R or PV which is equal to, I can write nRT, where n is the number of mole. So that is what I can expect, that is a P, that is a PV which is equal to, I can take n into R into P, where n is the number of mole, and this is a generalized equation I can write for your ideal gas equation. And one more thing we can expect, that is nothing but so this n can be replaced by, we can expect that we'll see the well And if I continue this equation, that is PV which is equal to N into RT, I can take as, let us write PV which is equal to N into R into T over here, where P is the pressure, P is the volume, N is the number of mole, and R is the universal gas constant, and T is the temperature. So now I can write N which is equal to, that is the small m by capital M, where M which indicates what? The mass of the gas, and capital M which indicates molecular mass. That is the molecular mass, where M is the molecular mass, where N is where small m which indicates mass of the gas. That is N mole of gas, the N mole of molecules in M number of M mass of M of a gas. So similarly, I can take one more relation, that is N which is equal to, that is N by Na, where Na is Avogadro number, and this capital N which indicates number of molecules in M, number of molecules in a particular gas. Okay, where N is the number of molecules in a gas, and Avogadro number, what is the value I can expect over here? What is the value of Avogadro number we can expect? That is the Avogadro, where Na we can call it as the Avogadro number. So these relations we suppose remember for a further discussion, where Na is Avogadro number, where N is called as number of molecules in small m, which means number of molecules in a gas. So that's what we can expect, where N we can call it as the number of molecules in M, in a mass M gas. Well, so this is what exactly we can expect. What is the value of Avogadro number we can expect? Avogadro number value we can expect around, that is Na we can call it as 6.023 into 10 to the power 23. So this is what exactly we can expect. So since these are the numbers, there is no extent for this. Just a number. These are the molecules. Okay. So these many numbers we have. So now the thing is, substitute this n value in the equation. That is, let us say it is the star equation that we have got under the ideal gas equation. So if it is so, what is the relation I can expect? PV is equal to, that is N by Na into R into T. Now if I plug this, because R is a constant, Na is a constant value, I can take as PV which is equal to N into K with the V subscript, that is a Kv into T, where Kv we can call it as a Boltzmann constant. Which constant? Boltzmann constant. Where Kv we can call it as, that is the Boltzmann constant. What is the value we can expect? The Kv value can be taken as Kv which is equal to, what is the Boltzmann constant? That is R by N into A, which is equal to, what is the R value we have over here? R value, that is nothing but 8.31 divided by, what is the value we can expect for your Avogadro number? That is nothing but 6.023 into 10 to the power 23. So altogether we can expect around 1.38. It is 1.38 into 10 to the power minus 23. When it goes to the numerator, minus 23. What would be the SL we can expect? That is nothing but joule per Kelvin. So how joule per Kelvin? Because 8.31 is the joule Kelvin per mole, and Avogadro number is this. So this is what exactly we can expect under the concept of your Boltzmann constant. Similarly, we can expect the relation which you got in terms of Boltzmann constant, Avogadro number, as well as universal Gauss constant. We are supposed to have an eye on all the topics, right? So these laws, these expressions we have got in terms of three different laws. That is nothing but Gauss law, that is the Boyle's law, and the Charles law, and Gay-Lussac law. Well, we'll see what exactly the Dalton law of partial pressure. According to Dalton, what he said to us, the total pressure in the mixture of ideal gases which is equal to the sum of partial pressure. In the sense, if you take one chamber and which consists of different kind of gases, and that particular gases which is equal to the total pressure of that particular gas which is equal to the sum of individual partial pressure. In the sense, for example, if I take examples like that is the basic formula, if I speak, PV which is equal to nRT, correct? nRT or nRT was a generalized equation as well, right? So now, what I do here is that I do in such a way that there are different kind of molecules we can expect according to the law which is given by your Dalton. Well, so if it is so, can I write the PV which is equal to, that is N1, N2, so on up to, that is N infinity. Correct? So into what I can write, or else I'll take this as for a generalized case as a mu, which your Dalton was used. So for that value I'll take. So that is like a mu1, mu2, mu so on up to mu n into r into t I'll do. Now, if I multiply your r and t inside the bracket, what happens? Can I write it like, it looks like a PV which is equal to, that is mu1 into rt plus mu2 into rt so on up to mu1 into rt. Can I write somewhat like this? Now you bring your v to the other side with respect to p, which means the total pressure is equal to mu1 rt divided by v plus mu2 rt divided by v plus what I can write, so on up to mu1 rt divided by v. And don't you think if each individual quantity which we have got in terms of individual pressure which is equal to, I can take, that is P which is equal to P1 plus P2 plus P3 so on up to Pn I can write. So which means the total pressure in the mixture which is equal, in the ideal gas is equal to the sum of partial pressure, sum of individual pressure. So this is what exactly is given by your Dalton version. Okay. So keep remember this. And next we'll move on to the ideal gas and some of the postulate which comes under kinetic theory of gases. We'll see what exactly the postulate which comes under kinetic theory, and it's the most important thing. And by using this particular theory, we are supposed to construct all the theories, all the ideas which is going to come up in the next class. So before that, we'll try to have an idea on the topic like a postulate or assumption in the particular kinetic theory of gases. Well, the first one what it says was that all the molecules of the gas which is having the same in mass as well as same in shape but differ in different gases. Which means if I take a hydrogen gas, all the mass of hydrogen of its molecules which is having the same in shape as well as same in mass, but there is a difference in oxygen as well as hydrogen. So each one which is having different molecular weight as well as atomic number, all those things. Similarly, molecules of a gas having the same mass and same shape of its own, but it is going to differ with respect to different gases. Well, and that is the first point we can expect. And it's the first point we can expect over here. And similarly, you see the next one, the size of the gas molecules are very small compared to the distance between them. In the sense, for example, if I take one gas molecule which is having a smaller size, whenever we speak about a gas, what comes to your mind? Obviously, the gas molecules are widely spread all over there. they are, which means interatomic distance between, for example, there is one gas molecule and here we have one more gas molecules. But think about in solid, they are tightly bound. Think about in terms of liquid, they are less tightly bound than a solid. But think about in terms of a gas, they are loosely bound. Which means, if I say these are the gas molecules, and it is widely spread over here. Now, think about the size of the gas molecules comparatively is negligible or less with respect to the interatomic distance between them. So the distance is large and think about its size. That is the one more thing we can expect under the second postulate which is given in kinetic theory of gases. Well, and third one we can expect gas molecules behaves like a rigid elastic sphere. What do you mean by rigid elastic sphere? Which means all the molecules for a time being it is moving with the constant velocity. That's the one more thing we can expect over here. And the second one fourth one we can expect molecules are always random in motion. Molecules are random in motion. Obviously, there is a loosely bound interatomic force we can expect in between two gas molecules. That's why. And move in all possible direction with all possible velocity. Well, and the fifth one we can expect during a random motion, molecules can collide with each other, and this collision is nothing but and this collision should be elastic collision. What do you mean by elastic collision, by the way? For example, imagine there is a wall over here, and this is a molecules. When a molecules when the temperature increases, what happens? This molecule starts moving. When this molecule strikes on the surface of the wall, what happens? Imagine it is moving with some velocity, and once it strikes, if it comes back with the same velocity, then we can call it as it is an elastic collision. That's why all the collision should be elastic collision. That is one more observation we can expect over here. And similarly, between the two successive collision, the molecules move with the uniform velocity. The distance between a successive collision we can call it as a mean free path. And the possible one mark section we can expect to define mean free path. So these are the concepts we are supposed to understand majorly under it is the kinetic theory of gases or the postulate. Remember the postulate? We have around 8. And these are the major 6 postulates that we can expect on the board. So these are the concepts we are supposed to deal under the concept of kinetic theory, and the remaining chapter or remaining concept we will see in the next class. Till that, thank you very much.